Welcome to Mr. Bernard's little miniature lessons on chemistry. Today I'm going to be quickly following sort of the order in which we put electrons into orbitals and the order of energy, and the order that they fill, and the order that we'd write them down in configurations. I'm not going to go into a lot of the three sort of quote-unquote names of the sort of rules and principles, but I'm going to hit sort of the high points and let you try and figure that out on the activities that you'll be doing over Tuesday, either in class or on your own, depending on if you're taking the test due to all the early outs or not on Tuesday. What you're seeing here is sort of the order of which electrons are filled. Now, it's based partly on the distance of energy of an individual orbital, and you'll notice some very key factors, like for every time you go up an energy level, you seem to add an orbital. What also happens is for every orbital type that you add, two additional of that type are added. So when we start down at the 1s orbital, there's only one 1s orbital and two electrons fit into it. So that orbital's filled. Electrons have to now go up to the next energy level, and that's a 2s. Two electrons again will fill into that. Now before they go up to 3s, there's a 2p orbital that now is opened. There are three 2p orbitals, one for the x, y, and z axes or planes. Again, two electrons each fit into each orbital, for a total of 6 electrons. If you count across the periodic table, the number of electrons on the first row is 2. On the second row and third row is 8. Fourth and fifth is 18. In other words, 2 from the S, 6 from the P, 10 from the D's. So there are 5 D orbitals with 10 total electrons. After that, there are 7 F orbitals with 14 electrons. If there were such a thing as G orbitals, there would be 9 of them for 18 electrons. If there's such a thing as an H orbital, there would be 11 of them for 22 electrons. Now, there is an order in which the orbitals are sort of filled. We try and read this chart as we start down here, we go up. Then the 1s goes first. Sorry about that. We go to the 2s. It goes back down to the 2p, the 3s. Back down, 3p, 4s. Back down. After the 4s comes the 3d, before the 4p. So it goes 4s, 3d, 4p, 5s. 4d, 5p, 6s. 4f, so that'd be the lanthanides that sort of stick out, the 5Ds, the 6Ps, the 7Ss, the 5Fs, which are those big radioactive elements, 6Ds, 7Ps, and these are predicted, but have yet to be observed. Could be partly due to the half-life, could be that they're just getting so big and massive that we don't know what's going on. But that's sort of the order in which it fills up when you have to go and start putting electrons into these things. How do you put electrons in? Well, it's sort of like this. As I was stating earlier, we'll put 2 electrons in every available orbital, and we will put 1 electron for every, and it's based on energy. We'll put 1 electron for every available orbital that is at the same energy level. So what that means is, it really doesn't really come into play until we start talking about the P's, the D's, and the F's. What will happen is, I would fill the p orbitals up with 1 electron each before I put a second electron in. We'll see this in some of the examples and some of the works you do. So I would put 1 electron in each of the D's before I put a second. And then we put in them by what's called spin. They're by convention. There's spin up, spin down. It really doesn't matter which one you put in first. Traditionally, we tend to put spin up in, but as long as the same spin goes in before the other one, we're all right. Let's move on to our first example. All right, if we were to write where the electrons were on aluminum, what we need to do is basically count the number of electrons that aluminum has. Aluminum is atomic number 13, so it'll have 13 electrons. We'll try and use this diagram, then we'll write out the configuration. We want to keep track of every electron, so it's just like it's saying, if I started at hydrogen and kept on adding one proton and one electron, what would happen every time? What we would do is we would write an arrow up and an arrow down, filling that orbital. Go up to the next one, up and down. We'd go over to the two p's, because that's what comes next according to our diagram, and we'd fill each one with the same spin. Then we'd go to the opposite spin. Right. 3, and last one, that'd be 13. And so we would write the configuration for aluminum as 1s2, 2s2, 2p6, 3s1, 3s2, 3p1. That'd be aluminum. Alright, fairly simple. We can do that. What happens if we go to something a little more complicated, like manganese? We'd do the same procedure. We'd want to account for every electron, and that has come before it. So we'd start by filling the ones down at 1, then we'd go up to the 2s, then we'd fill up the p's, all the same spin, and then we'd go the opposite spin. We go to the 3, S, 3p, fill across, same spin, 4s. Energetically, D's come before P's, at 3 D's come before 4 P's, and there are 5, and we have manganese. Alright, and so what would this configuration be? This would be a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Now you're asking yourself, why is this 3d after this 4s? Well, like I said, it has to do with the relative energy of the orbitals. While it's predicted that the D's should come with the P's, energetically they've discovered that the D's actually are slightly higher than the next row's S's. So this is sort of where it goes. Also, if you haven't quite figured it out, there's a layout to the periodic table based on the columns. The S's are basically on the extreme left-hand side, 2 columns. The D's and F's are that big block in the middle. The P's are essentially the block all the way over to the left. The periodic table is laid out by the electronic configuration. Alright, so you're asking yourself, that's a long way. What happens if we had a lot? Is there a shorter way to do it? Yes, there is. You basically go back to the last full row that you did, and you call it basically the Nobel gas. That sort of leaves you as saying aluminum, we could have also written it as having neon's configuration, then everything that came after it that was brand new. 3s2, 3p1. Manganese, it would have had argon's configuration, and then everything new that came after it. 4s2, 3d5. We can use this either way. We can be given a configuration, as long as we're told it's a neutral atom, and we can literally count based on this last bit of information and find out where it is on the periodic table. We literally can count over 7 electrons and be there, or 3 electrons and be there. Well, this is probably enough information for you to be able to start your activity that you'll be doing overnight after your test on Tuesday overnight, and that is due Wednesday. If you have any questions, again, always feel free to ask. We're here to help.